Alright, in this snippet I want to talk about glaciers. Glaciers are important for a lot of reasons. One of them is that they're a major eroder. They have a lot to do with scraping and digging and moving of material on the surface, which is a big thing globally, especially in the mountains. Bear in mind that during really cold times, of course, we have glaciers on land, continental at low altitudes, but generally they reside up in the mountains where it's always colder, and they hang out there, and they move down. And so a glacier is simply a large, long-lasting mass of ice formed on land that moves under the influence of gravity and its own weight. They form by accumulation and compaction of snow. So packed snow becomes firn, which is a crazy word. Then it refreezes to ice. So if you imagine snow getting thicker and thicker and thicker up in the mountains, what happens is that as it compacts, the snow becomes something in between snow and ice. It's snow crystals that are being squashed together, and then it gets completely squashed into really amazing ice, massive ice. So the idea here is that we start, for instance, up in the mountains where we're getting on top of the mountain, we're getting nice snowflakes. They start to compact, then they start to get to be something that's like a mixture between snow and ice, and then they become ice. This is pressure recrystallizing them. Just like we talked earlier about how pressure will change graphite into diamond, we can turn snow into ice simply by squashing it together. So then we can put the stuff up in the mountains, and then it starts to accumulate as a glacier and moves downhill until wherever it ends up. It could go down into the sea and then become an iceberg, or it could form with a bunch of others to make big continental glaciers. So we subdivide them into alpine, those that simply reside in the mountains, and continental glaciers, which can just cruise around wherever and wipe anything out. So alpine glaciers are found in the mountains, and continental glaciers exist where a large part of a continent is covered by glacial ice. It can cover huge areas. So about 30,000 years ago, all of Canada and most of northern North America was covered by glaciers. All of Great Britain was covered, all of Norway, Finland, Sweden, completely covered by ice. Okay, so here's a Davidson Glacier near Haines, Alaska. It's an alpine glacial system, and you can see how it is beginning up here in the high mountains, and then it starts to work into a glacier. Then it follows pre-existing valleys. So in all cases, alpine glaciers follow an existing fluvial system. So a system that's been cut by a river, we then just follow that down, and we change the shape of the valley as we do it by scraping away at the sides of it. Okay, so the idea here is we have things up in the mountains like an ice cap, which is on top of the mountain. We've got cirques, which we talk about in landform, which are where we get individual series of glaciers. And then these coalesce, cirque, they coalesce into a valley glacier, which when it's coming down onto land, we call it a Piedmont glacier. If it's going into water, we call it a tidewater for obvious reasons. And if it all accumulates into a big continental sheet, then that's a giant sheet of ice that just covers everything. So alpine glaciers are confined by surrounding mountains. So there's cirque glaciers, they erode basins of mountainsides. There's valley glaciers that flow into pre-existing stream valleys. And there's ice caps, which cover the entire top of a mountain. Okay, so one of the neat things is that these amphitheaters in the mountains are simply called cirques, and they are made by, let me get my pointer back here. For some reason I seem to lose my pointer occasionally. And they are made by, okay, what's going on? They are simply made by snow accumulating in the mountains and then carving away at the mountainside with the ice. So ice is a very powerful tool for gouging material away. Now let me see why I don't have, just bear with me for a second. I'm going to come over here. Ah, seems to be back. Is it over here? Well, that really stinks. Oh, I didn't want to go there. Sorry. I'm trying to show this amphitheater. So what you're seeing here up in the top there is a cirque, and then that was forming a glacier which came down and met a glacier that was forming in the foreground. So we had a glacier moving left to right here, and that glacier cut off the other glacier, and it left what they call a hanging valley. But those amphitheaters in the mountains, every time you see those, you know that a single glacier was there and that it was a cirque. Okay, I think I fixed my pointer here. So here's the cirque carving away. Here's the other glacier coming down, scratching these rocks here, polishing this wall, and cutting this off and leaving a hanging valley. These often, in later times, have waterfalls in them. Okay, so here's a cirque glacier coming down the valley and meeting up with a big valley glacier. And this is where you can see each glacier coming down and meeting, and a stripe of ground up material, right? Medial moraines forming between them as we come along here. So types of glaciers, we got the ice caps here. This stuff flows down, and then we have a continental glacier in Antarctica. Notice how there was nothing here except for a few little bits poking up that isn't covered with ice. So Piedmont and Tidewater is when we come down to the lowlands and then eventually come into the ocean. And then we get calving happening there, where we get big peats of it coming off and falling into the ocean, becoming iceberg. So we want to talk about the glacier's budget, gains and loss. Gains snow in the zone of accumulation up at the high altitudes. It loses ice in zones of ablation. As it's coming down and scraping rocks away, it's also getting scraped off. So it can be positive budget where it's growing. It can stay the same, or it can be negative. Remember, it melts from the bottom up, because it's always colder on top, so that as the glacier's coming downhill, it can actually be retreating upward because it's getting too warm out to carry on. So the idea is we always have gain up here in the accumulation zone. We have a region that's in equilibration, and then we get down to low elevations. We either come into the ocean and then we get calving and it breaks apart, or we simply get messed up at low altitudes because it's no longer hot enough. And then retreat would be when this moves upward, leaving a lot of the material that's with the rock. Now, something I want to mention here, because I'll talk about it later, is that if you imagine big boulders being carried by the glacier, as these chunks of ice come off and float out to sea and melt, the boulders they're carrying, they drop out as it melts, and these things bomb the ocean floor. And guess what we call them? We call them drop stones. And I'll show you a bunch of drop stones in later talks. I'm talking about Snowball Earth. But the fun thing about that is we talked about the equilibrium of grain size and how we have facies changes from boulders on land to really fine mud in deep water. What's interesting is we can actually move boulders out to sea, bomb them into the mud by glaciers, which is a really sort of disequilibrium situation. It's not carried by water, it's carried by ice. So that's something to keep in mind for later. So here's a cool picture. We're seeing more of this around the world, where we're chopping huge chunks of ice off into the oceans. So we see internal deformation where ice crystals slide past one another, and we see basal sliding where the entire glacier slides downhill on a thin film of meltwater at its base. That's a really neat thing, that it has meltwater at its base, and I want to talk about that. But glacier always flows towards the zone of ablation, always flow downhill. Okay, now anyone that knows me know I love phase diagrams. This is a phase diagram of pressure and temperature, and this is the water diagram. And it's just showing you that we have three forms of water. We have solid, the ice, we have liquid, the water, and we have steam or gas, the vapor. What's interesting about this is that these lines in space, they separate these different states of water. And three things we know about water is that if you live at 1 atmosphere, we know that at 1 atmosphere, the temperature of freezing is 0. You all know that. When it's below 0, we get ice around here. If we go up to 100 degrees, that's boiling. And this is an interesting thing because it shows us that as we go up pressure, the boiling temperature increases. As we go down pressure, the boiling temperature decreases. So if you live up in the high mountains, you have to boil your pasta longer, because if your pressure is lower, then your temperature is lower, so it doesn't cook as fast. Interesting thing. One of the things I want to point out here is the line that separates water from solid here has a negative slope to it. So we know that ice melts at 0 at 1 atmosphere, but if we go up to 10 or 20 atmospheres up here, it melts at a different temperature. So at higher pressure, the melting point has decreased. That means if we're at 0, but we're at, let's say, 10 atmospheres, then we'll find ourselves sitting in the liquid water field. So that's why at the base of a glacier, the higher pressure means that we melt the ice, so that we have a slick layer of water to move the ice on. This really helps us move things downhill. So this is an important diagram to have. You lower the melting point of ice with pressure. Really neat idea. And I could talk about this all day, but I won't. Okay, so here we have the accumulation zone. We come cruising down the ablation zone, and at some point we end. Notice here at the end is where all the rubbish we've been carrying piles up. That we'll see later is called a moraine. And as we melt backwards, we will leave a series of moraines shaped in that frontal lobe of a, excuse me, oh, sorry. I just paused my video.
Oh, I'm so sorry. I was on a Zoom a second ago as well.
Aren't you lucky?
Yeah, what time do you need me?
Oh, well, it depends. All I'm going to do here today is I'm going to make videos, because I heard a rumor that we're going to close up shop here soon. And so I want to get my videos made. So I'm just going to sit here and make these really simple videos that say, here's what a glacier is, here's what it look like. So I don't necessarily need your help, but I said to Tia that she better make those other videos quick. And I said, I wonder if Alicia could help you today, or if it's impossible.
No, I'm there. I'll get it sorted. Tia's in a meeting right now.
It's so boring that I walk in there and look at the poor deer sitting there listening to this bullshit on the Zoom. Isn't it amazing when you have a meeting on Zoom and you got nothing to talk about? I kind of like it because at home I can get a cup of tea or make some toast. But if you're trapped in a room, you have to listen to this shit. At any rate, I'm just going to...
I might see you a bit later on today.
Okay, I'm just going to rip out these videos, because then I'll have them. And then if I can't come in anymore, that's fine. I'll just post them. But I was thinking if you guys could do your videos today, just in case.
Yeah.
Because, once they shut her down, apparently, what I heard is it's not going to be like when the smoke was out and they sort of closed it and I came to work anyway. I think if they close it, they're going to say, you shall not enter. So, so Tia said she's got to talk to Luigi at 10:30. And then probably, I guess, from lunchtime, she'll be free to make videos if you guys can do it.
Yeah, 100%.
Beautiful. Okay, well, thanks. And we can talk by Zoom someday.
Yeah, that sounds really good. Good luck with it all. I'll see you soon.
Okay, cheers, bye.
Okay, bye.
Sorry, that was a phone call, but no worries. We're just talking about how stuff moves downhill with a glacier, and that basal sliding is something that I think is really cool, because the pressure of all that ice on top is changing the melting point of the ice right here at the base. So abrasion is a really neat thing, because rocks embedded in the glacier's base make linear scratches and grooves in the bedrock. Okay, and when we talked about glacial landforms, or we'll talk about it depending on the order you watch these in, these abrasions make really neat scratches in the rock, which we often call striations. And these scratches, you can look at rocks. It's almost amazing if you look in Minnesota or Canada or Finland or Norway. Many of the outcrops are polished beautifully by this, and they have scratches on them. So you can also quarry, which means you can pluck pieces out, remove blocks of rock, transport them downhill. Okay, so I'll ask you questions about glaciers, but for now, that's all I wanted to get done. Thank you very much.